Okay, everyone. Thank you for joining today's University of Texas Energy Symposium on March 21st, 2023. I'm Kerry Keene, Assistant Director and Research Scientist at the University of Texas at Austin's Energy Institute. It's my pleasure to have with us today Stuart James from Germany. But before I introduce him more formally, we'll indicate the upcoming 2 Energy Symposium talks. Next week will be a talk from Sarah Jordan, who is a professor at McGill University, and she will talk about life cycle assessment of the energy transition. And then the following week, 2 weeks from now, will be April 4th, will be Lisi Kroll, a professor of economics at the State University of New York at Cortland, and she will talk to us kind of about a high-level framework for thinking about energy and the evolution of human economic order. But as I mentioned today, our speaker is Stuart James. He is a research associate for energy system modeling at Deggendorf Institute of Technology in Germany. And the title of his talk is PyPSA, or PyPSA, PyPSA Meets Earth, a Vibrant Open Energy System Model Initiative. So slight background on Stuart. He's a mechanical engineer like myself by training. He used to work for Europe's largest industry association, VDMA, which promotes mechanical engineering, industry, machines, and equipment manufacturers. And he's now focusing his work on Sustainable Development Goal 7, SDG 7, which of course is affordable and clean energy. So he's working to make that a reality. And today's talk explains his work, which has started in understanding the energy system of Southern Africa and the Open Energy System Modeling Initiative there. And we'll hear how that has been expanded to other areas. So as abstract, what is energy system modeling? Why is it useful? So they'll take a deep dive into energy system models and how they reflect, or perhaps don't reflect, real world systems, and how we use this information to think about a global energy transition. He'll give us some insights into the open source movement behind this effort. And this is because this is an independent research initiative in an open source context. So we will learn how to run these large open source models and how we can organize ourselves for these kinds of purposes. So with that said, I'm now going to stop talking and hand over the screen to Stuart. And as usual, everyone on the call, please submit your questions via the question and answer feature of Zoom or on YouTube, and I will try to ask these questions at the end of the talk. If you have a question that's a clarifying type question in the middle, I can try to interject and give that to him as well. With that said, Stuart, the floor is yours.
Yeah, thank you so much for the introduction. Also, thank you for the invitation. I think most has been said about myself, so I'm very happy to just jump into what I'm going to present today. And basically, this great open energy system initiative that's been going on for around 2 years now. First of all, we are going to look into the background. Energy system modeling, what is that? Why do we need it? What does it do? And second point on my agenda today is the magic of open source. So why is open source such a great thing, especially when it comes to energy system modeling? And the third point today is basically also the title of our talk, on my talk, PyPSA Meets Earth. What is that? How do we work? How does the model work? And what have we done so far? All right. So let's jump right into it. Energy system modeling, what is that? When we look into Wikipedia, we can see that they define energy system modeling as a process of building computer models of energy systems in order to analyze them. So we take a real-world system, simulate it, and then we analyze it. Tom Brown, professor at TU Berlin, he says that energy modeling is a computer modeling of the conversion and flow of energy to meet people's energy service needs. So basically electricity, transport, heating, production of industrial goods. So this is 2 definitions about right. And what we basically do is we have this real world system. Here we have a nice image from NASA. Also open source, by the way, provided, and it basically shows the night lights globally. So here we have a real world system, and the idea is in such a simulation, we can basically model these electricity networks, especially, and can basically have like this simulation. So why is this done? Why do we need energy system modeling? So basically, to break it down, really helps to bridge the gap between engineering and decision making. So looking back at Wikipedia, these models often employ scenario analysis to investigate different assumptions about the technical and economic conditions at play. So what we do is we have a certain future that we want to look at. We want to figure out what is the best way to build an energy system. And we have different assumptions. And we use these assumptions, and then we test different options, and we can then compare these options, for instance, and then give those options to decision maker, and he can basically decide what's going to happen with them. Why do we use modeling here? Why don't we just build it? Well, it's a lot cheaper, basically a much easier way than just building stuff. So outputs that we can get from these energy system models are basic system feasibility, economic feasibility. That could be, we can calculate greenhouse gas emissions and compare them between different scenarios. We can look at the financial costs. We can look at use of natural resources and energy efficiency. So basically what these energy system models enable is basic system operations, engineering design, like a smaller scale maybe even, and the other one is energy policy development. And that's like a very important part that's becoming more and more important. Like we mentioned, or you mentioned before, like the energy transition. So there's a lot going on in that direction. So generally, energy system models enable informed decision making before we build these energy systems. So, I mean, moving a bit back, why do we do energy system modeling? Well, we don't have to talk about that, I guess. Our current energy system choices are not really doing it for us anymore. So we can see the correlation of temperature and CO2 concentration in the Earth's atmosphere. So since the Industrial Revolution, there has been quite a release of CO2 emissions from fossil fuels. That's basically in a geological instant. So we do have the problem that we have climate change, and so basically that's why we do this. So what's happening now is the dawn of another energy transition. So we have had a couple of energy transitions in the past. And this is actually why energy policy development is so important today, because there's actually a great need for systematic evaluation of options for the coming energy transition. And now we actually have the option to look into it. We're not going to make the same mistakes as, for example, in the 1900s, where we had the great idea to use whales for oil. Then we drove them to extinction, and they basically lasted for around 10 years or something. So now we have like the foresight. We can actually model what do we actually have, which resources do we have, and this is why energy system modeling comes in very handy today. So basically, we started out in 1850 or up to 1850. We had basically we relied on a 100% renewable system with windmills, animal power, and biomass. And then we moved into the coal direction in the 1850s, starting then. And after that, we moved more into the crude oil and natural gas usage of energy. And so right now we are here between this fossil fuel based energy system and a renewable energy system. Renewable energy system, basically the energy system of the future. And what we have here, we do have a certain image, what it's going to look like, which technologies we're going to use. But obviously there is many different options. So there's a lot of scenarios, a lot of different options that we can consider. There's a lot of different technologies. So the question is, what's the best mix? Also depends on where we are looking, what we are looking at, etc. So basically the question is, which pathway do we actually choose for this coming energy transition? And this is where we need energy system modeling, because we can basically, depending on the location, depending on the scope of our studies, we can look into many different scenarios and what might be the best options for this energy system that we're looking at. Exactly. So generally, how is energy system modeling done? A slice of theory. So we do have data requirements. We need to input the energy demand that we expect, energy sources, costs of infrastructure, and weather time series to figure out, like, okay, renewable energies, what makes sense. Then we have software requirements. We need software to process raw data. We need software to simulate or to optimize the energy system. And we need software to process and visualize the results. And in the end, results are usually published in reports in scientific journals. So basically, breaking it down, we have input data and a configuration, then we process this data, which means that we download it, we filter it, we combine it, so we make it usable. And then we create the model and we solve it, and then we get the results. So this is basically how we go. Now we're going to look into the magic of open source. So why does it really make sense to use open source when we look at energy system modeling? There are good reasons. Looking at energy, we will realize that there's high social, political, and economic relevance. It basically drives the world. There's a large role of business interests, big uncertainties about the future, and there's many trade-offs beyond cost, so environmental trade-offs, socioeconomic trade-offs. So there's a lot at stake here. There's a lot at stake. So computer modeling is actually needed to avoid bad investment decisions and to save the planet. But the results are strongly driven by inputs and assumptions. So what you put into the model basically already kind of decides what will come out of it, at least up to a certain scope, right? And if you have closed source models, you can't look behind it. You can't see what are the assumptions. You heavily rely on, what the makers of these studies actually tell you, that it's, basically true. I've read enough studies in my time in the industry association where I really did not know where these results came from, because they had a closed box. They didn't open up their data. They didn't open up their models. So there's no chance you can actually question these results, which is not the case with open source, because with open source, you basically have an open system and you can basically look into it. So what makes open modeling open? Basically, the entire modeling chain, it's open. You have open software, which you can look at. You can basically contribute, you can code, you can download it, install it, you can change the code. You have open data. So anything that also goes into the model, into the software, that's open, that's openly available. And the publishing is also open. So it's also open access. So the whole modeling chain is basically transparent, which enables you to really, if you wanted to, you could really look into it. So really anybody is free to download, inspect, process, share, modify, or redistribute the software, the data, or publications, basically. So that's the whole idea of open source and open source energy system modeling. And this comes in really handy. For which reasons? Transparency can literally change the game here. An increase in transparency also means that these results are reproducible, credible, because people can question them. Very important, and also mentioned very often, like in any kind of open source process, is the idea that you have less duplication of effort. If someone's already built it, you don't have to start from scratch. You can stand on the shoulders, on a giant's shoulders that way around. So basically, that's a really nice thing. That's also something that I'm experiencing right now as a PhD student, also, because I've basically started modeling with little to, well, not that much previous experience, and I'm actually realizing these models, they're really strong. So there's only minor adjustments that, again, they take a lot of time, but I don't have to start at scratch, and that's a really nice thing. Also, I don't have to pay like 100,000 euros or dollars per year for a license, or my university doesn't have to do that. So that's really nice. Then, as I just mentioned, allows a high level of customizability. That means you can take the parts of the model that make sense to you, you can change them, or you can add new features. And also, if these features could be useful for someone else, you can upload your code, and it will be reviewed and might become part of the mainstream. Yeah. And then, obviously, quite an obvious one is you can improve research quality through feedback and correction, which is actually a really nice thing. You can't do that with closed source models. There could be a mistake in there. Like there could also be very big mistakes in there, but nobody could really tell because they don't know what went into the model. So that's also something that's quite useful, especially when we're looking at these big tasks of energy transition. It's quite important, I guess, and having a lot of people actually looking into it, that would be that makes a lot of sense in my opinion. Also allows easier collaboration. You can, as I said, you can download the source code. You can use it. You can collaborate with the people who actually use the source code. There's forums, there's Q&As, FAQs, etc. And something that's also recommendable or also really nice is that you can increase public acceptance if you have like difficult infrastructure trade-offs. So just imagine you have a community, and this community has like a couple of options. They need a new energy system, and then we look into these different options. And if you have someone who can actually check like what went into the model, you have someone who actually can look into the code. It's that there's more trust because it's not closed. Yeah, and that's what we're saying. Openness basically eliminates the black box, meaning that yeah, it's fully transparent, and we can therefore always look behind the model. Okay, jumping into PyPSA-Earth. Basically, that's the initiative that I'm happy to be part of. It's basically an open source energy model initiative. And here is a brief history of what happened in the past 2 years and what we actually do. So we actually started out as PyPSA-Africa. That was in 2021 at some point in April. Basically all started with someone with Max Partzen from the University of Edinburgh, who had this idea. He was actually using PyPSA-Europe, which is basically the foundation, or like they actually made the groundwork for PyPSA meets Africa and PyPSA meets Earth. And he thought it would be a nice idea to actually use this model, use the basic framework, and generate get some new data and basically apply it to the African continent. So that's where we started. In 2022, the initiative basically extended to this global level, yeah, that was 2022. So basically what this is, it's a planning and dispatch tool. It's an energy system modeling basically. It's built on top of PyPSA-Europe. That's what I've already mentioned. PyPSA-Europe was basically built by Tom Brown, the guy I quoted, the professor I quoted in the beginning. And we have a very active and strongly growing user base. So there's a lot of PhD students. There's a lot of, there's also a couple of master students who are trying to do to write their thesis. But there's also a lot of companies and NGOs and think tanks that are starting to use it. For example, Fraunhofer Institute in Germany. We also have this think tank in Germany, which is called Agora Energiewende. They are doing quite a lot of good stuff, and they are actually also intending to switch to open source using PyPSA. So it's actually really growing strong. And it's basically like the tool development is quite continuous, and the support is really, really great. So if you're in the field, or if there's anything you would like to do with energy system modeling, this is probably the tool to go, because if you have a question, something doesn't quite work, you'll get support like usually within a couple of hours. So that's really, we're all really thankful to have people who actually want to use this, and actually who join our vision that open source energy modeling is something that we want to use in the future. So how cool are we? Looking at the GitHub Stars, that's apparently some sort of measurement. They actually indicate the user popularity and adoption, and here we can see of all ecosystems for open source long-term energy planning, which PyPSA belongs to. PyPSA is basically the most popular one. So a lot of people use it. A lot of people are basically in this community, which makes it very, very nice to collaborate, because you easily get help, basically. Our areas of engagement. So we kind of split it up in 4 here. So I mean, basically the one important one is our model. By the way, the PyPSA-Earth is the name of the initiative. Our model is called PyPSA-Earth. So just like a small differentiation there. So that's our energy system model PyPSA-Earth. Then to solve these to basically solve, we have like separate solvers. We are currently supporting an open source solver called HISE. They are trying to get some funding so that they can, increase their performance, etc. So that's something that we're also involved with. Then a very important part is data, creating open data, predicting data, and the whole data workflow. That's a very, very important part. The other one is the user and developer community, so that we actually collaborate. We basically also, last year we met in person in Berlin, at TU Berlin, and that was actually really nice to see like what different users actually do. We also had a PyPSA user meeting by the end of last year, so the community is really big, and the exchange is great. There's a lot of dialogue, a lot of collaboration, and also training. Training is very important. We have like a lot of YouTube videos. There's always more coming out that actually go through how the model works, because obviously you would have to get into coding. We don't have a graphical user interface yet. That's something that is being considered, actually. So, but it's really nice to work with these people. So our modeling framework, how does PyPSA-Earth actually work? Okay, can I use a pointer? Not sure. Doesn't matter. So we basically spoke about this earlier. We have the input data and configuration, the data processing, the model creation, the solving, and then we get the results. So this is basically what it looks like in PyPSA-Earth. In the beginning, we have like this process or this rule called build shapes. What does that do? It basically cuts out the region that we're looking for. So we have certain maps. that we use. And if we just want to look at Africa, we basically cut out Africa and apply this to all other rules that we have. Then we have one thing here called download OSM data. We use Openstreetmap data, which is downloaded, cleaned, and from that we generate basically our power network. We build power plants. We all use that, and here in this step we basically have our renewable energy profiles, which are being built, and then we basically run the model. That's basically how it works in general. Picking out a few, so the rule build shapes.
Stuart, this is Kerry. Can I just ask
Yes.
one question? Can you state again what OSM data is? Does it mean something particularly specific or a specific source, or what does that mean?
Yes, so OSM stands for Openstreetmap. So it's basically an open source. It's basically an open source data provider, you could say. So you can get a lot of data there. It ranges from so we get our power plants data from there, so we know like what type of power plant is in which location. We get our basically also our grid data from there, so we know where like our grid lines are from in which locations. So they have a lot of data that they actually can offer. So that's quite a good source, our main data source.
Okay, thank you.
Yeah, you're welcome. Exactly. So looking at the build shaped rule, so we basically take this from outside. So this is basically the input. We have like the world country shapes. So if we just want to look at a specific country, we basically use that to basically cut out anything else that's below it. So that's how you can imagine it. I mean, you have like this data which always is attached to a certain location. And if you just want to look at, let's say, Madagascar, you would cut out everything else because that you don't need that. And the same goes for these exclusive economic zones. They are needed for basically offshore wind. So it's basically the shorelines, you could say. Another one that I just picked out here is the build power plants one. They use they use basically conventional power plant capacities and locations, take that from an online database, and create a CSV file. And then basically this is what it does. Now here the build out or the cutout was Europe. So this is what you get in the end with all the locations. So you have hydro, nuclear, lignite, natural gas, hard coal, oil, etc. And then you can see like the different locations. So this also goes into the model. Then the other one, the renewal profiles that are built. This data also comes from certain data sources. We will look into like the different where we get our data from later. And you get like, for example, if you have protected areas, obviously you don't want to put your wind turbine in a protected area. So this would also be cut out from your cutout basically. So this all goes into the model, and then you can see here what we have here. This is the basically the potential for renewable energy in like a certain location, which you can see here. So this is just another way of showing how this works. So basically the model consists of the framework and the data, and the framework basically entails PyPSA, the code, and the solver. So we use open source solvers, but there's also a possibility to integrate commercial solvers, and then we get outputs. But very important is this field, like the data. That's something that we work heavily in. So we need infrastructure data, environmental data, socioeconomic, and then we have other inputs such as technology costs, fuel prices, maybe even policies and legislation. If we, for example, in Germany know, okay, like a policy is that we won't have nuclear power. I think like this is the last year actually. They're going to shut off the last power plants, so there won't be any nuclear power. It's just not going to be part of the model. So that's basically, these basic assumptions go in there. Right. So is PyPSA-Earth just another modeling tool? No, it is not. As you can see here, like most of our work is like regarding data handling, and that's actually quite interesting. We'll look into like a project that one of our members is actually involved with a bit later. So which data do we use? So for climate and environment, we use ready to open data sets, ERA5, etc. We account for land use restrictions and protected areas. So if we have like certain areas that that need to be used for agriculture, that's also considered, or can also be considered. And then we derive our power grid topology from the crowdsourced Openstreetmap, which I already mentioned. That's basically the main data source. We get data on generators from Openstreetmap as well, but also merge it from different sources. And then we have the power demand. That's a bit more complicated. So we use a global energy GIS, but we're also developing machine learning methods designed for global use. And that's basically the PhD project of one of our members, which we'll look into a bit later. So that's actually quite interesting. And there is a lot more in the development. If this is interesting to you, always reach out. So last year, we actually wrote a paper and discussed our model and how it compares to other models. And we also did like a small demonstration for the country of Nigeria. Exactly. And so this is basically one of the outputs. We basically modeled the country. Here you can see the optimization results for, in this first image, for 2020 power system with like electricity cost, levelized cost of electricity of 59 euros per megawatt hours. And then we modeled the 2060 power system, did some optimization there. And yeah, we get like, so our result is that it's a bit cheaper, but so it's basically just a demonstration that the tool is ready to work. And so it can be used, data can be input, it can be modified. And yeah, so it's being used, it's stable and running basically. So question is, why should anyone bother about all this? And in order to look into that, I thought it might be quite nice to actually look into actual examples of what two of our members have actually got out of this. So Albert, he's a nice guy. He's also from the University of Edinburgh. What is in it for him? Yeah, so it all started with a student project that became all too relevant. Basically, Albert supervised a Zambian master student from Zambia, who had general interest in the Zambian electricity market and the challenges around it. That was the basic idea. And then this happened. Zambia to commence power cuts due to low water levels at main power plant. So this happened in December 2022. So that was quite, they suddenly had a highly relevant angle on which they could formulate like a research question. So the proposal then was study how the future power system could look like, making it resilient to drought. So this started as a student project. What are the challenges in this power system? So only 34% of the population have electricity access. The network will need to be upgraded and money needs to be spent wisely. So this calls for optimization. So what they did was some long-term infrastructure planning with and some operational studies, and they used PyPSA-Earth. And out of this student project, they are actually currently developing a real big project, a proposal for like a big funded project. So that's one example. how PyPSA-Earth has been helpful already. What is in it for Lukas? So Lukas is the PhD student I talked about. So he has projects in like the whole artificial intelligence part. Works a lot with GIS also, and so his background isn't necessarily any classical energy related field, but he's very interested in this AI part. So his first topic was detecting infrastructure in remote areas. The second one, predicting demand, basically. And the first project was called Retackle Detection of Individual Towers. What towers are we talking about here? So you can see an image, and you can see, or maybe you cannot see, some power lines and some towers appear right there. And what he's working on is basically detecting these towers using artificial intelligence. There's currently 3 developments there. It's basically a grid infrastructure data set by Duke University. They take satellite imagery released by an NGO for humanitarian purposes, and actually can practice their AI model on this. And yeah, so there's a lot of research advances in machine learning. So this is also what's going on. So this actually feeds in on the data side into our model. And then there's the other topic, the demand prediction, machine learned based demand forecasting across Africa. First step, they look at the country level demand, then downscale it. And in the end, they basically aggregate this data, and it can also be fed into PyPSA-Earth. So there's like also these types of projects going on. Okay, so another question would be, what is in it for you? I would say a lot of opportunities, depending on your background, depending on whether this all might have sounded interesting. I mean, there's always the option to find a PhD project. There's a lot of a big network, really. If you've always been looking into, always wanted to have those code development skills, that might also be a nice option to look into a project. But in my own experiences, it makes a lot of sense if you can actually use it for something like some sort of research, which would be really meaningful. You can find a supervisor, you can have a good time. That's obviously also something that's a very important part of this type of initiative that depends on people actually using some of their free time to contribute to this type of modeling. But also, I think maybe one of the most important bits that I've, like, at least in my experience, you'll definitely expand your global network. You can get in touch with some really, let's say, at least in the modeling world, so some high-level people who have been in the energy modeling for like decades, and these people always know other people, and it's very helpful. Actually, one of our members just recently mentioned that they actually found like a job through like contacts they found over our initiative. So there's a lot of good opportunities here. So what do we offer? I mean, obviously the world's best open source energy system modeling initiative and model, says me. There's also a lot of other energy system models out there, but this is the one I know, so it works really well. Definitely quick support. I'm really surprised how fast the responses are. So if you have any questions, you asked on like in our Discord channel, it usually takes like up to like 3 hours, and there will be a response. Yeah, so that's really fast. And I mean, obviously any of the above. You just need to make it work for you. If you would like to join the initiative. Exactly. So how do we communicate? And also how do you reach out? GitHub is basically where you can find our source code. You can find our installation instructions, issues, reports, and feature requests. You'll find a very good, the instructions are really good. So that's where you find that. Discord is our basic like general communication channel. So that's for general discussions. When we collaborate on papers, that's also where we just open a new channel, and then we discuss it there. It's also really efficient, and people really look into that, and so it's nothing that's asleep. It's really vibrant. It's really alive. This whole initiative. And then obviously we have a really nice website, so check that out for a first overview. And exactly, Google Drive, we use that for minutes, presentations, etc. LinkedIn, we actually developed that like right in the beginning to have like some sort of outreach, which worked pretty well actually. It's a really good platform to get out there, I guess. And YouTube, we have, I think, like we must have like over 10 instructional and tutorial videos by now, and also like the talks that we had in the past. Exactly, and then we have a PyPSA list for general updates. But usually we like Discord is the usual place where we actually communicate. All right, so for me, join us and become part of a vibrant community. Thank you very much. I hope you could see me the whole time. I don't see anyone here, so it's a bit weird, but thank you a lot for your attention. Here is my email address in case you want to reach out to me, stuart.james@dh-deg.de. Thank you so much. And any questions?
Okay, thank you very much, Stuart. There have been a few questions submitted here, so I will go through them. The first one you started to address actually and discuss it. So someone was asking relatively early in the presentation, can this be called transparent artificial intelligence? And at least you referenced some applications for advancing algorithms or the field of artificial intelligence in general. Is there anything else that you might say about machine learning, artificial intelligence? Or I presume the solutions you are solving for in terms of dispatch of electricity power plants or the building out of electricity power plants going into the future is maybe using the least cost optimization and not really like a, artificial intelligence to solve for that. But anything else you might want to say or correct me?
Yeah, absolutely. So it's also, I mean, obviously it's also open. So that's like the idea. We have one, so if there's general interest, I mean, I can always also reach out to our members who are working on that. But it's like a really big part of what we do, open AI basically. I'm not that much of an expert in that particular field, but I'm always really happy if there's like particular questions to reach out to the guys who do it.
Right. Okay. So it would perhaps be safe to say that if someone had the wherewithal, they could download the tool and say, you know what, I'm going to change the algorithm that solves for the best mix of power plants and try to use some new novel algorithm or something, and it's open source. So if you can figure out how to program it, you can do it, right? Okay.
Absolutely. It's always welcome. Yeah.
Great. Okay. Here's another question. Is there any input information now, or you could discuss if people are thinking about this going forward, about material constraints within how the model solves for future scenarios like materials, minerals, manufacturing capability, anything like this besides, say, the actual renewable resource or just cost of fuels. Any insight there?
That's actually a very, very good point. Also considering the whole situation with critical minerals and rare earth minerals, I feel like that is something that would absolutely be worth looking into in such energy system modelings. As far as I'm aware of, it's not being done at this point in the model, but then again, obviously, if you have a research question that deals with these questions, it is absolutely doable. It is absolutely something that we can use as an input. So mostly these things are not considered actually right now in energy system modeling. But yeah, but it's right. It's very dangerous to not consider like these bottlenecks basically. Like especially for critical minerals, that's basically something that where I think it could be very interesting and would be a really nice research question to actually look into that. Yeah, because there is a lot of studies that have shown, like in the recent in the last 2 years, that this is actually a big concern. Yeah, so could definitely be done. Yeah, would be really interesting.
Right. I agree. And for that person who asked that question, I can say that's a large part of my own research, at least on the scale of macroeconomic modeling. That's sort of a higher level than grid modeling. It's a sort of full accounting of energy and material flows along with money, so we can understand at a high level these kinds of constraints. It's harder to get to specific minerals. And there are people working on that, like the World 7 model, World 8 model for.
Is that the system dynamics model?
Yeah. Those kinds of things.
Okay, that's interesting.
Yeah, Sverdrup, he looks at all of these kinds of things.
I actually studied system dynamics with him. That's so interesting. Okay,
Yeah.
Cool.
There you have
There's
it.
a connection. Super interesting. Yeah,
All
because
right.
we were actually, so something that I'm also considering for my PhD is like the combining maybe these techno-economic models with these socioeconomic or macroeconomic models. So yeah, that's very interesting. Good to know.
Okay, good for that person to ask the question, to let you and I need to follow up on that perhaps. So here's a question about this kind of, so Texans over here, we think about our electric grid that's separate from the rest of the country for the most part. And we get somebody from Germany. People want to ask questions about Germany. So there's a question about nuclear. You mentioned its last plants are being closed down.
Exactly.
This is just a question. Have you modeled, or has anybody used this model to understand sort of the reliability of the electric grid, and I guess Europe more generally, or at least meeting supply demand within Germany, or comparing with and without nuclear? Or is anybody, do you have any insights, or is anybody kind of using this model for that purpose?
So basically the previous model, the PyPSA-Europe, actually has been used by grid operators in Germany, not only, but also on like a European level. And yes, that is being looked into. And there's a lot of other studies that actually conclude that at least energy security right now is also, like, considering like the nuclear phase out is not that much of an issue, but actually PyPSA, like not PyPSA-Earth, but PyPSA-Europe has done that and has been used by a lot of also big players in the European context. Yeah.
Yeah, I'll just expand on a further question about this. Maybe goes to the next question online, but is there any details you can give about sort of like the time step of analysis, or the granularity of the electricity, modeling in that sense? Like, how many aspects of reliability can the model give insight into, or is it dispatching like every hour or something like this?
That's a good question. So what I can say in that regard is that at least what I've heard, like it's high resolution. I have no clue what that exactly means, but hourly is definitely something that can be considered. It always depends on the input data. So if you have input data that goes like even closer to like maybe even on a minute scale, that's something that can be done. I'm not sure like how it is like right now. Also like the spatial detail, I mean, that's pretty good. I mean, it always depends on the computational power you have, but I know that it can go pretty much pretty down, depend on the input data. Yeah, but that's a detailed question. So whoever's interested, just reach out. I'll connect you to Max, and he can tell you about it.
Great.
Yeah.
All right, here's a sort of related question. I'll kind of read it here so I get it. There are many energy system and electricity models, and a few go by names of switch. I'm familiar with that. And then there's URBS and TMOA. I'm not as familiar with those. So this questioner is wondering how a person getting into this knows how to choose the best model. I guess you've stated PyPSA may be the best model, but considering the need, how does a person avoid digging into all the models to understand which one to use, right? There's some time to learn them and then a time to figure out which one to use before that.
Yeah.
Do you know of any kind of summary papers that discuss comparisons between these models, or any insights, or how long does it take to maybe come up to speed with running PyPSA for a novice?
Yeah, this is a very good question, because I started in this initiative because I was just interested, because I found it interested. I saw a presentation on the initiative, and it was kind of interesting, and it opened the door into like this whole community, also scientific community. So I've been asking myself this question pretty late, because in the beginning I just didn't understand most of it. But it's a very valid question, and I think it really depends on where you are and which region you're trying to look at. If you are also curious to develop something where the groundwork has been done, but it hasn't specifically been tailored to your region, then it's definitely worth looking into PyPSA-Earth. If you are not that curious, I would probably start with looking at what is the region that I'm actually looking for, and is there maybe even a regional open source model that I can look into. But then on the other hand, I think really important, like the factor that you have a community that actually helps you. I've experienced that's super important, because you get quick feedback if you're really using it, because I mean that helps us. We're really all very invested in this. I think that could be, at least for me, that would be like a very important thing. Also, it's if you're a student, if it's like it's very easy to get in touch with us. I'd say it's very it's not very formal. So I feel like this whole situation with PyPSA-Earth would definitely be easy on beginners, although it does take a bit of time to get into the model. But then again, if you have coding experience, I had none, still got into it. It does work, yeah. So I would definitely recommend the one that has a good community. And as far as I've seen, like we have a good community. There is, like, also in our paper, we did a comparison between PyPSA-Earth and a lot of different open source models. I'm very happy to share that paper later.
Okay, that would be useful. You can, send me the link, and the person asking the question can perhaps follow up with me to get it if they don't email you directly, Stuart. So Carrie King at mail.utexas.edu. So maybe we can model Texas. I know some of us here on campus have models of sort of the ERCOT or the Texas grid, and this could be another tool to do that. Here's a question a little bit specific about what goes into the, I guess, solving. This is the optimization kind of speak, or objective function that's within the optimization of, say, solving for future electricity grid mixes. Do you have insight or knowledge about kind of what the objective function is? Like, is it, minimizing net present value cost over 30 years at some discounted rate, or do you have anything to add there?
So it basically does a cost optimization. What exactly, I'm not quite sure, but it does cost optimization is basically what it does. So it's a techno-economic model, I would say. Yeah.
Okay, very well. So this may be just a question for me in terms of Germany. Is there any kind of regular, hang on. Okay, sorry about that. So is there any use of this in other kind of, I don't know, national scope questions about the future of energy in Germany and use of this model? Is it integrated in the federal government in any way, or do people in the federal government regularly consider people using this tool as providing inputs? I can say this, if I were to stereotype maybe some views of here in the US, they would say, well, look at Germany, look how bad their energy policy has gone. But I think oftentimes when I hear Germans speak, they don't say the same thing. Look how bad our energy policy has gone. They say, no, it's going about how we might expect, and I think it's going okay. And maybe nowhere is having a harder time dealing with the energy situation than Germany in the industrial sector, and used to be sort of part of the industry organization for the industrial sector. So any insights you can give us in the use of this tool and informing German policy and current challenges?
It's a very good question. Yeah, especially the part regarding like the industry. It was a very big discussion. So for this tool particularly, PyPSA-Earth has been used by some local grid operators. Agora Energiewende, that's the think tank that I mentioned earlier. They are actually like right now pretty close to the governments. Like they had like a that basically the chief executive officer, he basically switched into the energy ministry just after the last election. So that's quite interesting. So that has been going on, and this is actually also the think tank that is considering to use PyPSA-Earth, but for studies outside of Europe. So yeah, so I guess that's just part of the scope. I mean, it's PyPSA-Earth, but the PyPSA-Earth has actually also been used. I'm not so sure about like the connections to like, I mean, obviously policymakers would probably read a lot of studies, so maybe it has had some influence. But I do know for sure that that think tank is considering to use PyPSA-Earth because they basically want to switch to a more transparent model. So yeah, it is actually out there. Maybe another word on the industry part. It's very interesting because a couple of years back when I was with the industry association, I was part of this group of like representatives, industry representatives, who basically created this Boston Consulting. They helped us create like a study that looks into the future of the energy system, and that was so interesting because all these industry representatives, because they actually were in this whole process, they actually started to realize, wow, this is going to be quite the transition. This really is going to change a lot. So it was very interesting to see how like these representatives basically changed mind, or basically said, okay, yeah, this is how we have to go. This is the path we have to take. So there's no way around it, I guess. Like even industry would see that right now. So that's very interesting.
Okay. Well, thank you very much for those insights, and thank you for joining us today. It's been Stuart James, Research Associate at Deggendorf Institute of Technology. Thank you again for joining us today, Stuart.